I will describe the project, but before I describe the project, I'm also going to provide a whole bunch of data that we've collected in the greater Boston area on projects as well. And if you were expecting to see Wystan Carswell up here, I apologize. I am not Wystan Carswell. She had a beautiful baby girl about a week and a half ago, so I'm filling in for her. So what I'll do is I'll talk a little bit about excavation-induced soil movements. More specifically, we'll jump into some case studies from Boston and the greater Boston area and some data that we've been compiling over the years. I'll kind of present the data, go through it a little bit, and I'm sure later on, if you want, we can have all sorts of good conversations about it. So when we're talking about excavation-induced movements, what are we talking about? For this group, it's probably pretty obvious. You have some sort of supportive excavation system, some sort of wall that's holding up the soil and the water. You want to dig a hole. Well, what's going to happen outside of that supportive excavation system because you dug this big hole in the ground? And we have to look at things like the lateral pressures, water pressures, surcharges that are around it, whether that's construction or existing buildings. And it causes, simplistically in my mind, two different kinds of movement. One is what I'm calling local movement. Put pressures on a supportive excavation system, pressures on a wall. That wall wants to bend in and move, and that's going to cause some sort of movement outside of, or behind, rather, your supportive excavation system. You can mitigate that by stiffer walls, more bracing. But the other aspect of excavation-induced movements is this concept of global stability. And what I'm talking about here relates specifically, I'm talking about it as it relates to the greater Boston area. But what we find is that we tend to have these global movements in where we have deeper soft soil deposits. Now I'm going to use soft soil deposits in quotes. I'm talking here about the Boston blue clay soil deposits, and what we consider for soft Boston blue clay may not be what you consider as soft soils or soft clay. But if you think about it conceptually, you've got a sponge. If you take a sponge and you put a pot on top of that sponge and then you lift the pot up, well, that sponge is going to expand, right? It's going to come back to and be like, oh, yes, no more weight on top of me here. Well, our clays in Boston do a very similar thing. As we excavate all this overburden soil off, we're going to get that bottom to heave. We've proven this. We've put extensometers in the ground, kind of measured ground heave as we were making excavations. And as that ground comes in, it's got to come from somewhere, and it's coming from outside of the excavation. So what we've been seeing, or what we've seen over many, many years, is that what you might predict from these local supportive excavation movements are really the impacts stretch out farther. And we think that's from this kind of global effect. And some of that relates to factors of safety against global stability. I'll talk a little bit about that. So how do you predict, right, excavation-induced movements? Well, the software folks here will tell you the more information you have, the more accurate those models are going to be. It's great if you know the soil profile and geology. I was talking to Bud over here, and he was talking about, well, not only do you need to know that soil profile and geology, but the timeline and when this all was deposited. And I hope that was a real good input or a comment as well, because that can affect how this soil behaves or performs. What that soil is, properties. So we do lots of lab testing. We'll do lots of field testing to try and get that. Groundwater conditions, pretty important to know that. You can get started into details about stress histories. Again, it goes back to the timeline of when soils were deposited, when construction happened. Geodesign, the last session, was talking about modeling the tunnel before they even started modeling the project to understand that stress history of the soils. Pretty good idea if you want to know how you're impacting adjacent structures to understand a little bit about those adjacent structures. And then how this thing is going to be built. As a designer, we have most of the time relatively limited input into how this thing is going to be built. We do know the site size and shape and the depth of excavation, which is incredibly important. We don't always know how it's going to be built, how long it's going to take to be built. The models that we tend to use, or H&A tends to use, doesn't take into account that time-related effect to the most part, for the most part. That's something that needs to be considered. And just those contractor means and methods. So how are we doing this? Well, I'm going to spend a little bit of time with some case histories to kind of give you a feel for that empirical correlations. What's this past data that we have? How did things perform? Can we use that to predict the future? I'm going to use those of you who know the Clough and O'Rourke paper from 1990 at that special ASCE conference. There's kind of a seminal paper, and they've got a whole bunch of plots in there. I'm going to kind of incorporate some of those. So that's kind of useful and quick, these empirical correlations. Doesn't cost much money. Don't need to do much lab testing in the field. All the way up to, two-dimensional, three-dimensional, finite element, finite difference programs, where great programs, we use them all the time, can produce unbelievable results, but as I'm sure most of you in this room know, garbage in, garbage out. You put bad information into the computer program, you're going to get bad results. And then there's, a whole bunch of other simple models out there that are more specific, beam on elastic foundations that you can use as well. And, really, where your project is, if I'm doing a soldier pile and lagging wall in the middle of a cornfield in Iowa, well, I may not need a Plaxis analysis to do that, as opposed to if we're in downtown Boston with a whole bunch of sensitive neighbors around us and transit, probably a pretty good idea to do a pretty sophisticated model and get some good testing. So now I'm going to go through some case studies. And the case study that we actually gave these folks over here is one of the ones in here, and I'll talk a little bit about that. But I think it's important, and if you were in the last talk, I talked a little bit about the typical Boston profile, and the last project I talked about was on that colonial shoreline or that neck. So what I have up here is kind of outside of that historic 1630, which I'll show in a minute again, colonial shoreline, what we typically see for a typical Boston profile. Got some fill. Filled lands can be filled in a variety of different time periods and a variety of different types of fill material. And kind of that marshy, organic-y material. It can be anything from a peat to an organic silt or clay. Sometimes we get this marine deposit, kind of sands and silts. And then the very famous Boston blue clays, up to or over 100 feet thick. It has this nice clay crust. If you look at the side, I actually included an example CPT or tip resistance from a CPT. You can see there's this clay crust on top. We could talk about why that's there, and it kind of decreases in strength as you go down within it. Eventually, it does get a little bit better. But what we see is when we have these thicker clay deposits in the softer clays, that it's kind of susceptible to those global movements, and we got to pay attention to that. So again, just real quickly, the green line, or the green highlight rather, is the old, we'll call it good ground. That's Allen's rock-hard glacial tills. And then outside of there is all the filled lands with the various filling times and different materials that were used to do that filling. So what we did for this presentation is try to come up with our own empirical plots. So we went back through our archives. We pulled out 21 projects that were specifically deep excavation projects, which I'm defining here as anywhere from 20 to 75 feet below ground surface. Just reinforced concrete diaphragm walls, slurry walls. They ranged in thickness from 2 feet up to about 4 feet. And we pulled all this survey data and all this instrumentation data that we had on these projects, about 100 structures around these 20 projects. So, each project had about 5 structures around it. And then, over 1,000 settlement points, surface settlement points, and structure settlement points. So, I don't know, do the math there. It's about 10 per structure. And so the first thing we did, was plot it against that seminal Clough and O'Rourke paper for stiff to very hard clays, which is kind of what those Boston blue clays fall out in, where they took settlement, this is, vertical settlement, versus normalized over the max excavation depth. And then the distance from the excavation that had occurred, again, over that max excavation depth. So the black dots are the Clough and O'Rourke dots, and one of the projects that they use is actually a State Street project. It's these open squares, which is in Boston. It almost seems as if it kind of informed their zone of influence line of about 3 times that excavation excavation depth. So you can see a lot of our data plots out in there, but there's a fair amount that's plotting outside of there as well. So if I kind of blow this up a little bit and give you just a little bit more background on this, this is all performance of adjacent buildings, or structures more specifically. The circles are spread footings, kind of shallow buildings on shallow spread footings. Triangles are mats, diamonds are tunnels, and then we have the little pluses, which is that Clough and O'Rourke State Street line, along with that Clough and O'Rourke line in there. So we kind of drew our own line for the greater Boston area, showing that we start to see these movements or these effects up to maybe 5.5 times the distance away from the site as that excavation depth, a little bit greater, kind of those global movements. As another little piece of information here, we also kind of divided it up into what I'm calling conventional construction, which is the open symbols. That's install your supportive excavation system, start to dig down, install bracing, temporary bracing, then coming back up out of the hole, as opposed to the solid circles, which were top-down projects. That's where you use the permanent floor slabs as your, not only your permanent bracing, but also your temporary bracing, a stiffer system. So that was all, fine and good, but we wanted to look at it a little bit differently, because that plot is all based on the height of your cut, the total excavation depth. But a lot of these foundations are buried for these structures. So we did a little bit more math, and for instance, some of these shallow spread footings, if we had a 24-foot excavation and we had a building that had a shallow spread footing that was buried 4 feet in the ground, kind of modified that H and used 20 feet. So kind of subtracted that out. So it was the distance from the bottom of those adjacent foundations to the bottom of our excavation to really pull into that kind of zone of influence. And since that H gets smaller, which is in that denominator, well, we're starting to see effects, or that zone of influence, going out now up to maybe 7.5 times the distance away. So when you think about these local movements, and we think about a 1-to-1 line or a 2-to-1 line from the bottom of our excavation, this is a lot different. This is a lot more. So it's got to be something else, and it's got to be some of these global effects, or at least as part of it. So just when I talk about zones of influence, we talk about a zone of influence line. You can have a bottom of the excavation or bottom of a adjacent building and draw up a line. It can be a 1-to-1 line or a 2-to-1 line. So wherever you think that zone is that's going to be influenced by the excavation, it could be drawn up from here at a 45 or as a 1-to-1. Or you can take your adjacent buildings or foundations and draw a line down and out towards it at whatever inclination as that zone of influence, just as a definition. So if I take that same plot I showed you before, where we've kind of normalized the performance, vertical settlement over here versus the distance, the normalized distance from the excavation, using this modified H of where the bottom of that foundation is, and kind of draw these. Here's a 1-to-1 line. Here's a 2-to-1 zone of influence line. And, maybe these spread footings up here, or we could kind of say this might be kind of that local influence in here. But there's a lot outside of there. Maybe this greater Boston spread footing envelope might be a little bit bigger. So we said, all right, well, we don't know exactly what the factor of safety is for this basal heave, but we wanted to see if we could come to any correlations between Terzagh's modified equation in here for factor of safety against basal heave and the performance of the system. So, not a lot of math here, but a little bit. So this factor of safety increases, kind of intuitive, right? If your soil is stronger, hey, your factor of safety against basal heave is going to be better. You got that in that numerator. Similarly, if the width of your excavation becomes really small, these trenches, we do for utilities, well, the factor of safety against basal heave on the bottom also tends to go up. That height of your cut, the shallower that cut, well, higher factor of safety is. And similarly, the depth of embedment, that toe below your bottom of the excavation, the deeper you drive that down, the harder it is for those circles to come around and affect that. And just as a rule of thumb at H&A, we liked in the Boston area, when we use this kind of simplified equation, we want to have our factors of safety greater than about 1.5. We find that if you start to get below that, you start to get some strain softening of the clay potentially. You start to get some, movements that are time related. So we try on average to stay above that. Doesn't happen all the time. So we, again, pulled out that Clough and O'Rourke empirical chart and said, well, why don't we take 16 of the projects that we have really good inclinometer data on? So we know how much that wall moved laterally over that excavation depth, and we know how they were built, or not how they were built rather, but what was used in building them. So we could plot their system stiffness, and as defined by this plot here, and pick off what that factor of safety against basal heave might be, and then let's plot it versus the modified Terzaghi factor of safety equation. And that's, pretty much a shotgun splatter if I've ever seen one. Couldn't really come up with a correlation there. That was okay. We took a shot at it. So instead, we said, all right, well, we have all this inclinometer data. What if we take this inclinometer data and see if we can correlate the lateral movement of the excavation support system to the vertical settlement behind the supportive excavation system? And, I'll have to admit, this was I thought this brilliant idea, and then a person in my firm by the name of Mark Haley, who's been around the block a few times, came up and was like, oh yeah, that's all we ever do. You take the inclinometer plots, turn them 90 degrees on your side, and that's how much vertical settlement you're going to get away. He said, all right, well, you're brilliant and all, but let's try this. I don't believe you. So we took some of these inclinometer plots, turned them on their side, and I'll show you just a couple examples here of that. And you can pay attention to this project. It may come back at the end of this talk. And so these two very different projects had very similar factors of safety against basal heave if you use Terzaghi's equation. This one happened to be in Boston. This one happened to be in Cambridge. Here's this one-to-one line. We plotted all these surface points and adjacent building points, took the inclinometers and turned them on their sides, and sure enough, plotted out pretty well. Did this for a whole bunch of projects, turned out very similar. So if we have good finite element analysis, just take that finite analysis, turn it 90 degrees for this movement, and here we go. We can get our movement away from it. Depths of the cuts were very similar, but we noticed one of the things that was very different was the size of the excavation. This was about 60,000 square feet as opposed to almost double it. Well, we did something very similar. I've labeled this as global and this over here as local, because that's definitely what we were seeing with some of these. Again, a different site, happened to be same site plan area here. This one was in Cambridge, a little lower factors of safety against that basal heave according to Terzaghi's, or modified Terzaghi equations. And you can really see that there is this global movement going out pretty good distance beyond where that bottom of excavation is. So we said, all right, we might be on to maybe a little something here. So we decided to then plot the maximum wall movement over excavation depth versus this factor of safety against basal heave. And then we created this little heat diagram of the size of the excavation. So these numbers are all colored. If you're colorblind, I'm sorry. We'll have to talk after. But from anywhere from about 20,000 square feet up to little over 100,000 square feet in some of these sites. You can see some of these warmer colors up here had the most movement of these supportive excavation systems. So some of that might be global, some of that might be some other effects. We also just plotted site plan area versus that movement normalized over the excavation height or depth. And you definitely can start to see a trend here. So the size of your excavation is the bottom line, is that it has an impact. So, why might that be? Could be some global effects. For the excavation, the wall movements, though, a lot of excavations in Boston in particular, we have a hard time using tiebacks. Hard to get rights to install under the city streets. We've got a lot of infrastructure and utilities, tunnels, can't use tiebacks. So we have to use internal bracing, or we oftentimes use internal bracing. Bigger the site, longer the spans are for those internal braces, regardless of the fact that we're preloading them. You do a little PL over AE, a little elastic compression, and that might have something to do with it. The other thing that might have something to do with it is I talked a little bit about that strain softening that occurs in the Boston blue clay that we've seen with time. Well, the bigger the site is, the longer it takes to excavate, the more you have those effects. So the bottom line for all of this, before I introduce this software problem that we gave, is that there are a lot of different factors, right, that affect how a supportive excavation system moves, why a supportive excavation system moves, why buildings settle away, or why streets settle, or infrastructure settles away from that supportive excavation system. And so you have to be really careful when you're thinking about this, when you're analyzing this, and when you're evaluating this. So without further ado, let's introduce this software problem that we gave. And as Ed mentioned, we were not real fair in the amount of information that we gave them. It was pretty limited. So it's the goal of this is really for education. It's not about getting the right answer or the exact answer that we got when we measured the inclinometers or those vertical settlement points or the settlement points on structures. It's really to demonstrate how these incredibly powerful software packages can be used, how technical experts will come up and talk to you about what they did, approach a problem like this, how they can badmouth the engineers for not giving them nearly enough information to do any of this work, and really just to show you how these tools are used and the benefits that they have. All right, so what was the project? Well, this is not some of the information we gave them, but I'll tell it to you anyway. It was a 30-inch thick, so 2.5 foot thick diaphragm wall over in the Seaport district of Boston, if any of you walked around there. We didn't tell them, but it had multiple levels of bracing, and this was one of those rare projects where we actually could use some tiebacks. So you'll see from the photo, we had some corner braces and some cross-lot struts, and then these big open areas. Well, in those big open areas, we were actually able to install tiebacks, and so it was, a pretty complicated site with different areas. The depth of excavation was about 39 feet. There were some areas that were a little bit shallower. And it was a pretty big site, or at least a pretty big site for Boston, almost 120,000 square feet. So what did we give them? Well, I gave them one boring log that had SPT data on it. So I know, real nice. We did manage to give them some excerpts out of, there was a special testing report done when the central artery came through Boston and was installed, in a similar area. That excerpts really just had some information on the Boston blue clay, some of the stuff that you see up there. I say CPT signatures. That's, really all it was. It wasn't CPT raw data or anything that they could actually do anything with. And then we were really nice, and we gave them this incredibly simplistic cross-section of the site. So here's our excavation over here, about 40 feet deep. We told them, we said, hey, there's another building nearby, 74 feet away. That building is founded on a mat down at about the same elevation as our bottom of excavation. That building has a 4-foot thick mat, and the bearing pressure on that mat's 4 KSF. And the size of the site over here, that adjacent building, is about 200 by 230. We did tell them, hey, we do have survey points on the surface and on the building itself. So what can you tell me? What can you tell me is going to happen? What type of supportive excavation system would you use? Or, you could just use a slurry wall like we did. How many support levels do you want to put in there? What might be the factor of safety against basal heave? Who knows? How deep do you want that supportive excavation system to go? And how is it going to affect anything behind you? That wonderful building that I had highlighted. So I'll give you the spoiler alert of what actually happened, and then I will turn it over and they can tell you all the good stuff that they did. So this is what actually happened out there. You can, if you see these inclinometer plots, they may look familiar from some of the other stuff that I showed before. In total, we had anywhere from about 1.5 inches to 3.5 inches of movement around the site. For this north wall in particular, we had between 2 and 2.8 inches of movement, as shown here. You can see we did have, shockingly, this is the bottom of that slurry wall. And we did have some deep-seated movements, about 1/2 inch, pretty good distance away. Well, if you were to take that and rotate it, as Mark Haley would like to do, even though this basement was at the same elevation as our bottom of excavation, we saw 74 feet away, up to about 1/2 inch of movement, a settlement of that building. Well, going back about 100 feet into it, we still saw up to about 1/2 inch. Much past that, started to taper off into about the 1/10 of an inch range. But that's what they got. We can now let them tell us. We'll start with Augusto here, and he can tell us what he did. Oh, and thank you for attending. Sorry. Oh, no idea what just happened there.
So yeah, this was an interesting challenge because they both mentioned we got pretty much nothing to work on. And as you know, one borehole and SPT in clay is not the top of the information that you may get or aim to get for a design like this. So I had to get a little bit creative. And as you know, I left the word preliminary. Everything that I'm showing here is nothing more than a really preliminary investigation from a numerical analysis perspective, try to assess what is the potential behavior of the system, try to look at the issue from different angles, looking from the data from site, looking at the literature. I will show a lot of data that I kind of investigated and taken out from the literature, and then compile a 2D sensitivity analysis with different solutions, and finally I also put together a 3D analysis just for, let's say, the sake of it, and because I was getting involved into this, and also because I was testing the new Flat 3D version 9, so I used this example also for internal testing for our software. So, okay, so let's get started. Damian already showed the cross section, the modification that I did looking at the borehole. I just modified the elevation. They provide 11.5, and I put it at 16.5, just because the top elevation of the borehole was at 16.5. So I don't want to even complicate even further. So I put an extra few feet. So everything is consistent with the stratigraphy that was provided, and obviously as a simple approach, I've assumed that this borehole is representative of this big, huge area. So this is the first big approximation that usually is not even remotely realistic. So then, as you will see, these are the elevation that I've identified and marked out of the stratigraphy, and the water table was put at minus 12 feet. And since I'm a CONED, I can't really do anything with SPT. I found a way to, nothing that I found anything is already in the literature, but the way I would approach this problem in a real situation is I would try to transform the SPT into CPT, and then correlate the CPTs with any type of parameter that I need for the numerical analysis. So as you can see, this is the typical correlation as a function of the particle size. We didn't have any particle size, but I look at the paper that Damian provided, kind of have a feeling for the conversation factor. So you see here the factor that I've used to convert the QC and the FS. These are the bottom unit. They're not so important, but I kind of went down a little bit in the model to try to see if there was a deeper effect in terms of displacement. There wasn't, but and also I tried to see what I was getting. This is just a zoom in into the QC plot. From a few CPT plot that I found from some literature in a nearby, I think. I'm not even sure if it's so near, but it's still in Boston. So I was getting relatively close results, let's say between 1,000. I'm sorry, I'm using SI unit. After 10 years, I still don't understand the imperial unit, so I apologize for that. So 1,000 and 1,500 kilopascal, we are probably in the same ballpark. And so I said, okay, this is a go. Let's go and use this CPT data along this data to get all the property. Now, as you know from the CPT, you can correlate a bunch of different parameters. I took a leap and imagined the pore pressure that the CPT was realistic for the site. So I made a lot of assumptions. But this is the density that I've used for the model. The estimated IC, why I'm bringing up the IC, because you will see that I kind of plug in the property of the constitutive model to the IC index and to the shear wave velocity. So this is the reason for connect the IC to the constitutive model property. The other, what you can see here in the green, those are the design line, assumed design line, the property that I attributed to the model as a table as a function of depth. Now, as Damian was mentioning, we need to have a little bit of a stress history of the site. So what you try to do, you try to estimate an OCR, and a K-note factor, which is very important because it determines the horizontal pressure that you have. And this was a really relatively good agreement with Mansory correlation. And also another paper that I found for another excavation, again in Boston, that was giving very, very good similar results to what I was getting. So I kind of gaining confidence, okay? Step by step, you look at the issue in different angle and try to gain confidence. I'm in the right direction, I'm totally wrong. And so I kept digging. And finally, I get to one of the most important parameter for this type of analysis, which is the soil deformability. So shear wave velocity, for me at least, is the starting point. If you don't have it, you try to push to have it, then ask a second time. But if you don't get it, you have to try to estimate through correlations, okay? So this is the shear wave velocity profile. I try to also push a little bit of some of the correlation that you would use in sand. In this clay, for example, as you can see, Orengoro, Yoshida, there were typical correlation for sand. So I took a little bit of a liberty here, and I'm not being very orthodox in the application of this correlation. But hey, it's an exercise. So you get the shear wave velocity, the G max distribution, and the G max over sigma prime V, which is close enough to the paper that I was showing earlier. And also, this is another paper that I found about geology engineering property of sensitive Boston blue clay. It was kind of giving a similar profile. So also this one was a go. Now, we didn't mention anything about strength. So undrained shear strength or effective stress strength. I personally don't use undrained shear strength in this type of analysis. I don't think that this is representative of the realistic, let's say, behavior of the soil. It is an engineering properties, but still, the shear strength is always related to the effective stress of the soil. So what I tried to do is to use information from Maine about the CPT estimation. I also pushed some of the correlation from SPT, CPT, and I was kind of getting a cloud of points that in my mind was making sense. So this green line is the one that I've used for the analysis. I also put a little bit of cohesion. Effective cohesion, at least at the beginning, as a peak strength, and then that would degrade if you get closer to or go post-peak, which we don't want to do, obviously. So for the formation, I've used 0.2 and 0.3 sigma prime P. Again, the reference is Paul Main and the research that he did in this type of material. This is also due to the fact that I never work in Boston. So I don't have the gut feeling for the behavior of this clay. So I have to do a little bit of homework to try to gain a little bit of confidence in what I was doing. Then I found some very interesting paper about lab test. So as you can see, these are shear tests, probably not the best, but I think they're good quality. They are showing I'm concentrating mostly on the peak strain. I want you to, let's say, pay attention to this one because we don't want to get into the strain when we do the model to go over this level because once the model starts softening, it's too late. But in terms of shear strength, we're getting good agreement with the CPT. Again, cohesion 0 and friction angle 31. These are the triaxial, which I would prefer, that are showing, let's say, a peak strain around 1 and 2%. And again, a little bit of cohesion maybe, and a friction angle of 31, roughly. So let's say anything between 30 to 35 for this clay is acceptable in my opinion, and probably even higher. Now, also plot the Aldrich strength because it's an information that you have to get, but it doesn't go in any way, shape, or form into the modeling. The other aspect is the consolidation, because in the model I also try to account for the time scale. So I try to mimic how much it's going to take to do this excavation, to install these anchors or this bracing, and so I would let the model consolidate for that time and then keep going with the extra excavation, a sort of a decoupled type of approach to see what is the effect of the, let's say, consolidation problem. Now, constitutive model. We have to decide what constitutive model are we going to use for this analysis. I mean, the simplest one is Moore-Coulomb. Of course, we are all familiar with Moore-Coulomb. The problem with Moore-Coulomb is if you are looking only at a loading problem, for example, this is a sketch of a footing, and we are looking for the bearing capacity, it's okay. Even if we are using a more sophisticated, elaborate model, we are going to end up considering the same friction and the same shear strength, we are going to end up in the same ballpark. If we are in a loading problem and looking only at the service limit state, so the beginning of the curve is still fine, but once we go and move ahead toward an excavation, the Moore-Coulomb doesn't have, let's say, a different stiffness between loading and unloading, so you have to decide which one to pick, and probably somewhere in between. And most of the time what I've seen is that you get an unrealistic uplift and an overestimation of this bottom heave that is most of the time not realistic. Beside the fact that also the bending moment, because you tend to have a more rigid deflection of the wall instead of having a more curvature, so you're also underestimating the bending moment. Anyway, enough for the Moore-Coulomb, so I decided to adopt the plastic hardening model, which is pretty standard, nothing too elaborate, but it's a good compromise between, this is a bunch of lists, I'm not going to read everything, all of this, but essentially is the most adopted constitutive model, let's say, without going too sophisticated for this type of analysis. I just want to highlight one of the most aspect, which is the difference between loading and unloading, and also the stiffness dependent according to a power law. And if we want to add, it's not for this problem, but if you have a compression problem, you have also a volumetric cap that is important also for compression problems. So this is what I was showing yesterday, volumetric cap. Here we are hardening in volume, and the magenta line, no, it's not magenta. What color is this? I'm kind of a blind here. Is the hardening, the friction hardening that is going to end up into the Moore-Coulomb criteria. Now, I got a question yesterday about how, don't read all the equation. I mean, the parameters that the model use are essentially this reference value, E50 reference, which is essentially the secant. So the black line is a Moore-Coulomb triaxial test, okay? The red one is the stress strain for a plastic hardening. You see that you have two different stiffness. One is the initial, then you have the loading, which is equal to the unloading for the Moore-Coulomb, and then you have the unloading, reloading for the plastic hardening. The way I look at this is I never give I try to estimate not the reference value, but the physical properties, 50, E unloading, reloading, and then the volumetric part. And then, since the model still wants the reference, which is just numerical modeling parameter, I reverse this equation and then give what the model wants. But me, in my mind, I need to understand what are the physical properties first, and then feed the model with what he needs. Anyway, long story short, essentially all those parameters can be estimated using the shear wave velocity, and then the material index. As you see here, there is the material index, the solid behavioral type from Robertson, and then there is a division factor that goes from the Gmax. You calculate the E unloading, reloading, and the E50 through these two divisors, okay? Those factors. And what I've seen in many applications, both in unloading, like an excavation, or a loading problem, is that if you are in a, let's say, solid behavioral type below 2.6, so the typical silty, sandy region, if you take something that is in between 3 and 3.5, you're going to end up having in the ballpark for the material. Once you go over 3 and possibly 3.5, then these factors here are becoming greater. So meaning that the stiffness tend to decrease for the material. So this is what I did and what I plugged in. The same story goes for the volumetric hardening. It's less important in this case. I was just trying to give an overall picture because it is an excavation. And then also the other parameter is the alpha is the shape of the cap that govern the evolution of the shear and volumetric hardening. There is a paper here published by, again, I think Paul Main, from which you can infer that probably a 0.75, 0.8 for alpha in these materials could be realistic, but you usually do a sensitivity analysis. The same for the M exponent, essentially 0.6 for frictional material and then go all the way up to 0.9 for clay material. And you can draw any line in between. Okay, next step, lab. What are we going to do with this lab? So the way I would approach this problem is once I have a stratigraphy, I determine or just select a few depth and then build a numerical virtual lab test. So these samples here are my, let's say, ideal or virtual test from which I determine a virtual triaxial test to see if the curve kind of resemble what I'm getting from the real lab. So what I'm looking for is not the exact matching. I don't care about that, but I'm trying to capture at least the peak deformation. I don't want the material to go over the peak deformation. And I have adopted two different hypotheses. One is H-stiff, which means high stiffness. And then, sometimes the material is variable. Actually, most of the time is variable. So I may have a different deformation. This is the same, but for, let's say, a shear test. So this is a simulation for a shear test, similar to the other one, so 2 to 4. And then for the low stiffness, essentially the peak strain goes, let's say, between 3 and 4. Okay, it's just an hypothesis. I know if it is realistic. It's just a kind of a design hypothesis to check during the analysis if this would still be applicable. Same for the low stiffness. Now, okay, let's go into, am I doing okay? So support analysis. Now we are starting the design analysis. It was all the premise about the geotechnical aspects. Now we are starting the analysis. So for the D-wall, I've used a 0.8 meter, which roughly I think is close to 2.5 feet, right? Then it is all nonlinear, concrete C35 megapascal, which is, I believe, 5,000 PSI. I investigated two types of embedment, 14 and 20 feet. And then this is the type of initial rebar, just for the nonlinear behavior of the diaphragm wall. In terms of support, I investigated anchors, 4 rows with different level of pre-stress and different level of bond length, and also 3 rows with different level of bond strength and pre-stress. This is a sketch of the 2.5D model, I would call it, because it's just a slice. It's not exactly a 2D, but it's a slide that encompasses 4 anchors. Now, these are all the cases, and so you see the name here that identify the embedment and the number of anchors and the type of soil. Okay, so just to have a sort of a library of different expected behavior. Now, this is the first one, which is, I would say, let's say the base case in which we have a 14 feet embedment, a soft soil, and 3 anchors. Kind of getting, let's say, 60-something millimeters, so 2.5 inches of displacement in this red region. You see the heave. If you look at the vertical, you see the heave, which seems a little bit, is more, let's say, pronounced, obviously, close to the embedment length because of the passive engagement. But if you give time to the model, obviously, this is a picture in time at the bottom of the excavation. If you let the model consolidate, the pore pressure re-equilibrate, of course, you will see even more. So there is no bottom slab installation here, but usually at some point you install the bottom slab, and that's okay. You can keep going without thinking about this problem anymore. So I stopped here, and I just let the consolidation for a few weeks after the excavation, just the time for the installation, and this is the picture. So I'm getting about, in this case, roughly 90 millimeter of heave for the lowest embedment. So the magnitude is even higher because there is a vertical component. Keep in mind that the other variable, which is very important, is the inclination of the anchors. Here I kept it simple. I just made a 20-degree inclination. But as you can see, there is a volume of soil that is highly disturbed because of the interaction with the bond zone. So a better idea in this case would have been to kind of go a little bit more inclined, get the bond zone out of this region, but then you may end up triggering a little bit something below the foundation of the building, which could be probably even worse. So I decided to stick with this. This was just an exercise. Nobody's going to build anchors close to a building like this. So it was just to see what would happen. The bending moment, everything looks fine in terms of bending moment. It's just a 340 kilonewton, which is nothing for this type of diaphragm. So usually in this type of situation, the bending moment for the structure is not dimensioning. Now, a bunch of plots that are showing the displacement. As you can see, we are not anywhere near to, let's say, the bulk of the displacement is happening, of course, between, let's say, 3 distance, but then this line is not at 0 yet. And I think this is probably 3 times, so I should have extended the model longer, let's say go further without any doubt. But considering that I didn't have any information about the structure and the displacement are getting smaller and smaller, because it's not the absolute value of the displacement that matters, is where if you have a sensitive structure where the patient rotates, and if you are losing tension in the foundation, not really the total vertical settlement, if it is even half an inch, probably you don't care because it's just a uniform settlement and doesn't provide any extra stress to the structure. But if you have rotation, for example, a building that would be here at this point, that half is hanging on the right side and half is going there, you may see some crack happening in that location. So it depends on where the building is located. And this is the eave behavior. You can see is more pronounced close to the diaphragm wall. Now, I'm going to go very quick here, just showing this is the evolution of the displacement for the monitoring point that we're given. So R means road. Obviously, this is going to go down. The bottom of the excavation is going to go up. The building, it's in between the 0.1 and 0.2 inch. So I'm talking about 2 to 3 millimeters. Obviously, you cannot see in this scale because, if you can see, this is 60 millimeter, and this would be, an order of magnitude less. Then this is, again, the same plot, but showing the horizontal displacement. Of course, this is way too high in terms of horizontal displacement, so not acceptable. And as you can see that we are probably in the order of, let's say, 8-9 millimeter of the building in terms of horizontal displacement. Now, I'm going to go very fast here because I'm going through the same slide for the different cases, and I'm going to show you the final table of this, which is the summary. So once you have compiled all the analysis, you come up with a table, and you have to make a decision. I'm going to go with 14. I'm going to go with 20. What is the impact of adding an extra row of anchors, and so on and so forth. So it looks like, looking at this number, essentially going from 14 to 20 feet, it improved the performance, and by performance I mean the global displacement, of about 10%. Yeah, maybe it's worth it, maybe not. Adding a row of anchors improved the performance of 20%. Adding a row of anchor increased the embedment is a little bit less than the sum of it, because there is interaction. So you don't get the 30%, but you get a little bit less. But if you are uncertain on the soil, stiff and, let's say, soft, you get 40-45%. So the bottom line is try to understand the soil before getting into adding row of anchors and stuff like that. So now, strength reduction, stability analysis. Once you have completed a model like this, I don't see any benefit in engaging limit equilibrium, with all due respect with limit equilibrium. But at that point, you just reduce the strength and see what is the strength reduction. By the way, I've implemented the strain softening, and you can see these little zone here, these are just starting to strain soften. These are over the peak, just at the contact with the embedment length. So what we get, I'm plotting the displacement of the wall against the strength reduction factor, which is equivalent somehow to the safety factor. For case 1 and case B, essentially, we get, these are the 2 different stiffness. The point of this one is just to show that once we get into failure mode, as we were showing with the comparison with more Coulomb and plastic hardening, the stiffness doesn't matter anymore. We are getting pretty similar, 1.18, 1.18 for both cases, which if this is a temporary structure, and if you, let's say, organize the construction sequence in such a way that you can put the bottom plug quickly, it would still be acceptable. So you can try to push it. I wouldn't feel so confident, so I guess this is with the 20 feet embedment. We get the proverbial 1.3. I feel probably better, and that's what I decided to stick with for the 3D analysis. I also analyze an internal bracing. The internal bracing behaves much better, as expected. We get much less displacement for both soils, and also this is just I don't pretend to be anywhere near close to the final configuration. I had no idea what was the configuration. So this was just my gut feeling and my assumption. I was pretending that this pipe would have been part of the final structure going up. So this would have been similar, let's say, probably to a top-down. Again, less displacement. These are some of the forces that you get in the struts. I also simulated a delta T effect. Sometime when you install these big struts in the winter, then, in the summer, then it gets winter, these tend to shrink and you accumulate extra displacement. So just to have an idea, in this case, the effect was in the order of 10 to 20%, which is not a small thing if you think about it. A 30-degree change could have an impact of this order of magnitude, which is similar to what you would get installing an anchor or not. Okay, I'm going to jump here and go for what I wanted to show here is this slide here, sorry. So this is the equivalent of strength reduction factor, so the stability analysis in case we use internal strut. So with the anchors, we were barely able to go to 1.3. As you can see here, we have a flat line, and then I stop it because there is no point, all the way up to 1.4. So of course, as expected, the internal strut, if you're going to pay a little bit of, let's say, organization of the construction site and a little bit of pain for installing all this, but in the end, you get a lot more safety. Okay, some stress resultant, I'm not going to get. Now, finally, 3D. I have 10 minutes left, so I'm going to show you a few slides of the 3D model. This is showing, I took the 20 feet embedment as a reference case, and also consider layout of support similar to what I would probably install in this case. So corner with braces, put anchors here, and then this is the internal bracing in this location. Each bracing is 10 meter, so 30 feet apart, and there are 2 level bracing and 3 row of anchors. I don't know how many you install on site. So just some information about the displacement. The maximum displacement that you're getting is where you have the anchors, because of course the system is softer, is not as stiff as the internal bracing. So we get about 2 inches of displacement. The other aspect is, in this case, probably is not so important, but in many cases, the connection and the interaction between the primary and secondary panel may be important. So I model also in this case, let's say, a discontinuity between the 2 panels, because you don't have passing reinforcement, right? So essentially, the joints can take bending moment as long as there is axial force. Otherwise, the bending capacity is very small, close to 0. And it cannot get any tension in case you develop tension somewhere, especially around the corner. So there is a special links that I developed in order to be able to capture this continuity aspect. The stratigraphy, of course, this is a very simplified hypothesis. In reality, you have a bunch of soil, like I was showing yesterday for the TPI project, in which you have way more information, and you can organize the stratigraphy in a 3D in a more realistic way. So this is just a very simple hypothesis. I'm not going to get into this detail, but essentially a construction sequence that I'm showing is each step, I'm assuming to excavate each layer for the whole site. Very simplistic, okay? Each layer is 0.6 meters, so 2 feet. And I'm assuming that the excavation time for each layer is about 2 or 3 weeks. I don't remember exactly. Now, this is what I get at the end. The eave that I'm getting, also because of the contribution of the piles that I'm putting, is essentially holding down the ground. I'm not getting a significant eave, and I'm getting a vertical settlements of the order of 30 millimeters. This is just a section in between that shows the vertical displacement. This is the Y displacement, which in this case is, let's say, 42 millimeters. And this is in the other direction, the short direction. I was trying to show the pore pressure, but I've not been successful. It's a very, essentially what you see is the pore pressure at the bottom, because this is an effective stress analysis. The pore pressure tends to drop, and so you may also develop, if you allow the model, also some negative pore pressure that helps stability. That will go away if you let time elapse. At that point, then the pore pressure will equilibrate. So this is a transient configuration of the pore pressure. This is an overview of all the structure with the displacement of the D wall. And you can see here, for example, that the links are capturing potentially the detachment of the forces that are happening because the structure is not continuous. And then a bunch of slides that are showing the stresses. I'm not gonna, these are just kilopascal, are showing the minimum principal stresses. I can't really skip this. I just wanna show this is the tensile stresses. You have a very low tensile stress. So everything is within the, let's say, domain of the structure. As far as the D wall is okay. The other interesting aspect of modeling the D wall discretely, like I did, is that you get the contact forces in between. So you can also manually check if you are okay with those forces and they are compliant with the ACI code or anything that you want to implement. These are the horizontal forces in the liner. Then as far as the MX, the bending moment is a little bit higher in this case than what I was showing with the 2D, but still way reasonable. And then the forces in the struts, obviously I didn't do a second iteration to try to optimize or anything like that, also because I would do that once you get the monitoring and the results from observation on site. And then you go back and reiterate and see what you can do. So these forces are compatible with the struts. So this is the guy that is taking a lot of heat there, even if it's blue, but it's the worst one. And then this is just another view that is showing a vertical view. And these are the forces in the anchor. Of course, the forces in the anchor is a function of the pre-stress. I put a lot of pre-stress in these anchors. And once you put the pre-stress, usually you don't see a significant amount of increase in force, maybe 10, 15%. But you try to lock in as much as you can without yielding, this, of course, the steel. Displacement, what I was getting, this is vertical displacement, so this is the eave. In this case, remember that I have piles who are holding down the ground, roughly 30 millimeters. And the building is moving vertically very, very little in this case. So this is something that is off, of course, with what you have said, which is totally fine. And the horizontal displacement is a little bit higher, is let's say 1/10 of an inch, something like that. Don't pretend you to read any of this stuff. I think that the most important, I would say that one closing remark, probably you say, how long does it take to build this model and to run it? Okay, so building the 2D model is roughly, took me, let's say, a week, all those suite of analysis, analyzing. Let's say another week to build a 3D model, and the running time is really not the bottleneck. So this is a 2.5 million zone, 200,000 nonlinear structural elements, and it run in less than 24 hours. So the bottleneck is not really the running time, it's probably on the side of the building. But once you have built the model, you have the capacity of doing so many sensitivity analysis and plug in multiple computers that you get, so many informations that I think is worthwhile. And with this, I think I'm 2 minutes earlier, so I'm leaving like this. Thank you.
All right, we're going to hold the questions. We're going to have a panel. Next, I'd like to introduce Alireza Azami with Rocscience.
Thank you very much. So we are dealing with the same problem again. It's a deep excavation in Boston. And I'm from Rocscience, and these are the tools that we have, and I'm going to use a bunch of them in this simulation. As for the problem, we have the plan view, we have the section, and what we are looking at is the formation, what is the behavior, and also we will be looking at what is the factor of safety. And the tools that I'm going to use in the order of that I'm using them and I'm setting up the models, they are going to be RS2, our 2D finite element program. Slide 2, limit group analysis, two-dimensional. Slide 3 is 3D limit group analysis tool, and RS3 is our 3D finite element program. So I'll start with site characterization, what we were given and what we could actually extract from it. So we had one borehole, which had given us the layer of the material, and we had where the water level located, so 12 feet from the ground surface. What else we had in that problem statement? We had a bunch of strength characteristics for some of the materials, and we had a special report that we had some, I couldn't extract any mechanical characteristic that I could use in my finite element or limit group analysis. So this is basically, if I go back, this is basically the information that I could actually use in my finite element and limit group analysis. So to fill in the gap, I did some research on, for example, this one, finite element modeling of a deep excavation in Boston blue clay. So all these articles that I found in the literature, similar problem, deep excavation in Boston. And one of the names that is actually popping up is this guy, Andrew Whittle. So I said, okay, these are pretty good references that I can take some material properties, some site specification from them. So looking at them and what I had, so those are the material properties that I was given, the black ones. And from the literature, I extracted those specifications like stiffness, K-naught, and the permeability of the material that I was going to use in my simulations. Even some of the strength characteristics, for example, I had to extract it from those literature. The good thing was that in most of those, I actually had the same layering of the material, so with the same name and all that, so I could trust that, okay, probably I am not wrong. For my first estimate, I can use those values, run my first analysis, and based on that, if I have more information, which I never got more information, I can calibrate my model and build on top of that. So I make my base. If I have more, I will build on top of that. So going forward, I will do the 2D one first. I will walk you through what is the process of setting up the model in RS2, how to take it to slide 2, and what are the results that I'm getting from this. So in RS2, first is the finite element analysis. We are setting up the project setting. I will use the imperial unit because you guys like it. Like my friend, I don't get these numbers. It doesn't make sense, register to my brain. SI units, I get it, but these, I'm still puzzled with them. So we will be using imperial units. I will do 2D plane strain analysis. It's 2D dimension, RS2, 2D finite element analysis. This is plane strain, which actually turns out to be a correct assumption when I compare it with 3D analysis. And to consider the hydromechanical coupling, what is the effect of pore water pressure and all that, I'm using the consolidation option with coupled and using the bioformulation. I'm using more than 20 stages for my analysis. The first one is going to be initial. I'm establishing the field of stress and the pore water pressure in the domain. Then I will have the wall installed. Then I have sequence of excavation. I will excavate every 2 feet in half a week. And I have stages that I'm installing tiebacks or support that takes 7 days. So this is going to be the list of stages that I will have. The way that I generate the soil profile in my model, I'm using that borehole that was provided to me. So that borehole is going to be giving my geology. For groundwater analysis, because I'm using that coupled formulation at the top, what I will get, I will have that transient analysis selected for me. It is grayed out so that I cannot touch it because I'm using that coupled formulation. I cannot touch that one. Just to be on the safe side, to be conservative, I'm removing the effect of negative pore water pressure from the calculations of my effective stress. And at the end of it, to get the factor of safety at the final stage of excavation, I'm activating that strength reduction tick mark so that it's going to run the SSR analysis and I will get the factor of safety. So in terms of geometry, the soil layers are defined with that borehole that we had. And we have slurry wall that is defined by structural interface. The structural interface that we have in the middle is consists of liner element to represent the wall, and we have that orange hash line that we have next to it. That one is going to be the interface element that we have between the wall and soils. And for the meshing, I'm using 6-noded triangular elements. I am refining it around the excavation for one round, and another round of refinement around the area that I have the wall and I have those support elements, anchors. For groundwater, if I need, I will do dewatering 4 feet below the level of excavation at each stage that I'm going forward. And I have the traffic load on both sides. I consider 200 pounds per feet square, and I'll consider in that one in the analysis as well. Now, to establish that initial field of stress, the water table was given. Initial condition that I assume for K0 from those articles that I found, the K0 is defined per material. I'm assigning those K0 values for them. And what I have, I'm assuming that the building next door and the traffic load are initially present for the initial state. And then second stage is going to be where I'm installing the slurry wall. Now, there are multiple options that we tried. We analyzed for the supports that we have, for a slurry wall and all the supports. The one that we ended up at the end of it using for the slurry wall was the thickness of the wall, 80 centimeter, 2.6 feet. The wall is going to be reinforced concrete. So within the dialog that you have in RS2, you can select, okay, this is reinforced concrete. You have the typical properties of concrete. I'm using that. And for the reinforcement, you can go to the library of reinforcement that we have in RS2. I'm using the rebar number 10 at 4 inches from the side. And the spacing along the length of the wall is going to be 8 inches. Depth of excavation is 40 feet. And I consider 2 different embedded lengths. One is 20 feet, one is 30 feet. The 20 feet is the one that we ended up using at the end of it. For the supports, I'm actually looking at the side that we don't have the adjacent building first. I will get my support from there. I will get my factor of safety and displacement there. And the other side that I have the building, I will use more support so that I will get less deformation. So I will analyze everything in this one first. Then using the analysis from this, I will add more to support and put it in the side that I have that building next door. So I have 2 rows of support here, 2 rows of anchors here. They are installed at depths of 9 feet and 29 feet. Again, I'm using that library that we have for RS2, this library of support that we have, the extra Aztec with 19 and 4 tendons. The tensile capacity is given here. I'm installing them at 30 degrees deep. They are 70 feet long. And the top row, I'm installing the anchors at 6 feet spacing. The bottom one, they're going to be at 4 feet spacing. They are pre-tensioned, close to 50% of the capacity, and the lengths that they are bonded also 40% and 50%. We considered other cases as well, when you have maybe a third row appearing at 19 feet depths. And this one, again, I consider 2 cases for it. If these anchors are installed at 4 or 4 feet spacing from each other, just to see if I'm adding more support, is it going to help me or not? Now, this is the library of the support that we have. If you go to common type of the support that we have for the anchors, you can select the manufacturer, select what it is, and the properties is going to be there. It's going to be included in the calculation, and that is going to be the anchor that you are using in your finite element simulation. Now, from left to right, this is the case that we had 2 supports, the top one at 6 feet distance, the bottom one at 4 feet. This is 3 rows of anchors, 6, 6, and 4 distance between them. And this is the heaviest case that we have, all the support. This is the heaviest case that we supported at 6 feet, 4 feet, and 4 feet support. You're looking at the horizontal displacement. The maximum that this one is giving us is close to 2.6 inch. This is vertical displacement. Comparing them with each other, again, this one is giving us the maximum. Well, this one is the weakest case anyway. Now, the bending moment, the shapes are representing how those anchors are actually adjusting the forces that we have, the bending moment that we have in the support. This one was the shape that we actually liked it better. It looks more economical, and the values that we have in this one is actually okay. These are the shear forces in the wall. And these are the forces that we have for the anchors. So the forces are, again, at the end of calculation, the maximum load that appeared in the support in the anchors is close to 50%, a little bit higher than what we assigned for the pre-tensioning. So it's a little bit higher than that, so the values match pretty well. Now, we did SSR analysis on top of this, so you can see that the factor of safety is 1.36 for the weakest case, 1.38, and 1.38. And these are the mode of failure that you see, how the total displacement looks like in Aldrich in these 3 cases. And if you're looking at the shear band, the failure zones, you can see that, okay, this is close to 45 degrees because this was considered as frictionless material, it's only cohesive material. So it makes sense that this is the shear band that is forming in this simulation. And what else is important is that, okay, this shear band is actually going through the length, the free length of the anchors. It's not going through the bonded lengths. So another indication of, okay, this design looks okay. Now, just to confirm that 1.4 that I got from finite element, the factor of safety, you can import those RS2 model to slide 2, the limit equilibrium analysis tool. The only thing that you need to consider is the structural element. The wall is not coming to our slide, so you will have to have that material zone developed for it to have the wall included in the simulation. And you can see that the factor of safety is 1.6 throughout all of them, for all these cases. We had 1.4 from finite element, 1.6 from limit equilibrium. They are basically confirming each other, looking at the fact that, okay, in RS2, the finite element, the forces of support are calculated based on the deformation. In this one, the forces of support are considered as the whole thing that is coming. So without the consideration of deformation and all that, you're actually using the maximum forces of the support. So basically, this one is giving the factor of safety higher than that. But as long as I know what it was, that was 1.4, this is 1.6, they are kind of matching each other. They are confirming each other that the numbers are not off, they're okay. To further confirm this one, this is Spencer method. If you're looking at the results for Yambu method, Yambu is usually the lower band of limit equilibrium analysis. This one is giving 1.2, 1.2, 1.2. So the factor of safety in all these cases, they are talking about the same 1.4 around that number. Now, if you are looking at the groundwater, so if this is the end of construction, if you have 2 years passed after that, and the water comes back where it was, it's trying to get back to the same level that it was before. After 2 years, I did another SSR analysis. The factor of safety is from 1.36, 1.4 is coming down to 1.3. So still, even after 2 years, when the groundwater is coming back, the factor of safety is acceptable. Now, we are looking at the bending moments of the wall, those 3 cases that we had before. And if you look at the maximum cases that we have for this one, this is the stage before the final tieback coming. This is the stage that we had, the final stage of excavation. If I plot them for the support capacity plot from RS2 using ACI standard, I can see that all those cases, they are actually within the envelope. So in terms of the wall capacity, we are also okay. In terms of displacement, the wall displacement, horizontal displacement, this is the final case that we ended up using in all the other simulations. So the maximum horizontal deformation is close to 2.65 horizontal deformation at the end of excavation when we had only 2 layers of support. comparing those three cases with each other. So the weakest case was this one, so 2.6 deformation that we have, horizontal deformation for that. If you wanted to extend the embedded length of the wall, these will be the configuration, the solid lines, and okay, more support, anchors, more support for the wall, you would get less deformation, it's gonna be more contained. But at this side, you will have a little bit more moment, but still these are in acceptable range. So what we took from this side of the wall, that we did not have that building next to it, this is the design that we are going for, that 2 rows of anchors, and the embedded length of 20 feet extended, 40 feet excavation, 20 feet extended embedded wall. Now, let's go to the other side. In this side, there are, again, 2 options that we will try. I increase the number of anchors just to be safe in terms of displacement. So this one, we have 4 rows of anchor. They are installed at 3, 11, 21, and 31 feet from the surface. The first row is not as strong as the rest of them. So this is 19 by 3. Capacity is less. The other ones are that strong support that I had on the other side as well. Again, similarly, the pretension is close to 50%. The bond length is also close to 50%. Second option that we tried, we removed this third row from the middle to see, okay, if 4 is good be enough, 4 is enough, or 3 can handle the same situation or not. Again, the one that we had 3 tendons, the properties, again, I'm gonna go from the library. I selected, it's gonna be there. I needed that first row, because if we did not have that one, I would lose the convergency. It would not converge. I would get the deformation around the wall and also the excavation. And I will use heavier anchorage, as I mentioned, so that I have limited displacement on this side. Looking at the values of deformation, horizontal deformation on either side of the wall. So at top of the wall, in this one, I have horizontal deformation of 0.16 inches. Next to the building is 0.6. I think that was similar to what was presented. I did not know, but I have the numbers almost matching. If I have 3 rows, so those values are a little bit different. At the top of the wall, I have more displacement. If I'm looking at vertical displacement, I have close to the wall, close to the building, I have 0.6 deformation settlement, and at the top of the wall, I have 0.9. Again, I think I remember it was something around 0.5 from the monitoring data. And if I have 3 rows, those numbers are almost the same, but I have a little bit more deformation. Looking at the bending moments, so this is the case that we have the maximum bending moments happening. For the case that we have 3 anchors, that at that stage I have the maximum. If I have 4, the maximum is more than 200,000. If I'm plotting those ones, this is the shear force. And these are the anchor forces. Again, anchor forces are close to 50% of the capacity in all cases. Now, if I go for failure mode, factor of safety in this one, again, is very close to 1.4. But since I have more support on this side, more of the failure is actually happening on the other side. So that one I'm okay with. And if I'm looking at the shear bands again at some SRF that is more than 1.44, you can see that this side is actually forming a more clear shear band and failure pattern comparing to this side. So this side with the force support that I added here is safe in terms of stability and safe in terms of deformation. These are the bending moments comparing the case that we had 4 rows of anchors comparing to the 3 rows. And if you are looking at the capacity of the wall, as I mentioned, in the case that we had 3, I had the maximum is more than 200,000. Hand calculation was giving something around 200,000 as well for the bending moment. So this one is not the case that we recommend. We will go with this one for the 3D analysis maybe. So on that side, with no building, we have 2 rows of anchor. On this side, that we have the building, we have 4 rows of anchors. So this is basically the final design that we came up with. In terms of deformation again, the maximum deformation that I have at the top when I have the wall, it's pretty small. Going down, I have larger deformation, but I was limiting the deformation at the top mostly. These are the bending, the shear forces in the wall. And this is the ground settlement on the side that we have the building. So ground settlement giving us close to the building minus 0.6 inches. Close to the wall, we have close to 0.85 inches displacement settlement. As for the heave, both cases they are giving similar distribution for the heave. It's going to be close to 1.5 inches with 3 or 4 rows of anchors. And something that my friend also mentioned, the importance of constitutive modeling. What we have in all these tools, like even RS2, we have an extensive library of material model. These are the one that we have, like PM4 sand, we have NOR sand, we have FLAC material models, we have Plaxis material model. These are all rather advanced and constitutive models. The only thing is that if you want to go use these, I actually developed these all myself. As a developer of these, I would recommend that, okay, you calibrate first, then you go use these. Otherwise, you're basically asking for trouble. So if you have something to calibrate it, you justify the properties and all that, okay, by all means, go for these. If not, keep it as simple as possible. Use as much information that you have and try to use reasonable values for those constitutive models. Something that could be useful here is, okay, we are dealing with excavation. What I can do to add to my more Coulomb material model is that I can add unloading modulus. So I can use a loading modulus. I can add a criteria for the unloading, which should be like mean stress, for example. Excavation, when you're unloading, you can assume a higher Young modulus. So I would assume that, okay, if I have my E unloading, is going to be 2 times of E loading, some general number, just to show you what is going to be the effect of that. So this is the previous case. E loading and unloading, they were the same. The other one shows E unloading twice of E loading. We are looking at horizontal deformation on the side that I have the building. You can see that, okay, the maximum was 1.8. Now maximum is close to 1.1. So like 40%, 45% difference, just easily by adjusting the material properties to something that could be more realistic. So this is a case that you will be needing to look at this one first as much as you can, then you go for all these support and all that. If I'm looking at the other side, so maximum horizontal deformation is 2.6 inch. If I have E unloading equal to 2 times of E loading, it's 1.55. Again, close to 40% difference. So again, another indication, do this one first as much as you can, then take it to the finite element. The heave again, maximum I had was 1.7. If you use that assumption for unloading stiffness is close to 1. And with that, I will take them to 3D models. So I'll start with slide 3. It's quite easy. You can just import a slide 2 model in this one, extrude it, manipulate the geometry a little bit, assign the anchorage from the library, again, from the same library. We have heavier anchorage on the side that we have the building. And this one, if you are looking at Yambu method, I'm getting factor of safety 1.31 for 3D. 2D was giving 1.2. So usually in these scenarios that you have a long structure, 3D should give you like 5, 10% higher, usually. Again, emphasis on usually. But the reason for this one right now is that, okay, this slip surface that is formed behind the wall and also coming inside the excavation area, at some portion of it, like for example here and here, it is going through different locations of the support. So if it was 2D, for example, your slip surface quite easily could go behind the support and come out from the other side. This one has to intersect with the support at some point because the shape of the bowl has to be formed, and then you have that mass that is failing, that failure body that is moving. And you can see it in other cross sections as well. So 1.3 versus 1.2, reasonable results. If you're looking at the safety map for this one, close to building, there's nothing serious happening. We have more of the heat or more of the lowest factor of safety at the free lens here, and also similar lens that we have here on that side, so close to 1.3 at the area that we have lower concentration of the support. And if I'm looking at Spencer method, which is supposed to be more accurate than Yanbu in terms that if you are having lots of horizontal forces coming in from the support, this one is giving 3D 1.8 comparing to the 2D that was 1.6. So looking at this moment, I can say that, okay, that 2D simulation that we had was a good assumption. So we didn't actually need to take it to 3D as much if we are going to do similar cross-section for the problem. Now, taking it to 3D, RS3, again, RS2 can be imported to RS3. You can extrude it, manipulation of geometry a little bit. You have the building there. Then you're assigning these support patterns at different locations. You're adding them. The tiebacks are going in. You're installing it per stage that you have. And you can run the simulation in 3D as well. This is the contours of horizontal deformation. If I make a cross-section through it, where I have in the middle of the building, and compare it with RS2 results. So this is RS2, this is RS3. This shape is almost this one, and this shape is almost this one. And the maximum values of deformation that I got is close to 0.22 feet, 2.6 inches for all these two cases, to 2D and 3D. So another indication, 2D and 3D in this case are very similar to each other. And these are the bending moments in the wall, comparing RS3 with RS2, similar shapes you can see here. And these are the support forces that we have for 3D compared to 2D. The values are very similar, except for this one that I had. This one is a little bit different, but the rest of the cases, they are very similar value that I'm getting from them. So as the summary, we use both 2D and 3D analysis. We use the finite element and limit equilibrium analysis on this same example. We looked at different support design and pattern, and we proposed different ones. We analyzed them all for this problem, and based on the stability and the performance criteria, we used the most economical design for this. We did a comparison between all these methods to verify them against each other. And the importance of the modeling and that initial site characterization was actually emphasized. So if you have more information to begin with, you will get better results, more reliable results at the end of it. And I'm going to give you the summary of what was the specification of the model that we had and how much actually it took for each of those runs. So for example, for RS2, to the finite element analysis, with close to 9,000 elements, 6 noded elements, 26 stages, plus SSR, those simulations will take around an hour. For 3D, 4.5 million. I reduced the number of stages. I just looked at the stages that I had the excavation and I had the support. 11 stages, 4 million elements. I need 3 hours. I didn't run SSR on that one. For limit equilibrium 2D, all these is less than a minute, all of them together. 3D limit equilibrium, Yanbu and Spencer method, it takes like 7 minutes. Okay. Thank you very much.
Thank you. We're going to have a panel now. Damian, if you could come up too, and Augusto. Huh? What are you talking about? Look, I'm even hooking you up. Look at that. So yeah, we would want to discuss kind of the presentations, the project, and have questions for the software providers. I wanted to kind of kick it off with a first question, which is probably, I think, probably the most important one, is what information. So if somebody out here is going to do a model like this, or hire you to do a model, what information do they need to tell the owner that should be required? You can say maybe this is some good additional stuff, but like, what do they need to tell the owner that's required? Augusto?
Yeah, so I guess you can guess what I'm going to ask. Sometimes I get it, sometimes I don't. Sometimes it's not possible. But I insist to have CPTs, possibly seismic, of course, CPTU. If you can, direct measurement of even cross-hole, or maybe downhole. Cross-hole is not going to happen, but maybe some downhole is more likely. But if the soil allows CPTs, I'm not a big, I would say, fan of lab tests. Some are useful, but I wouldn't invest, let's say, a big budget on lab activity in general. That's
And
my
you mean DMT too? Like, I mean,
Oh, yeah.
like the whole range.
The whole range of institute tests that gives you an idea about, stress histories, and you can interpret and correlate different properties in effective stress.
Well, I would like to have more of what is the specification that they need, what is the importance of these values that we are ending up calculating at the end of it. And I actually like the lab tests. So with the lab test, or
We're together. Look
Yeah.
at the lab.
it depends on the sophistication of the simulation and analysis they would need. So if going to use my advanced calculation tools, please give me advanced information so that I can utilize it. If I'm looking at stability, maybe from CPT, from SPT, I can get my strength of the material and run my stability. But if you need more of deformation, and if you're dealing with complex materials, I need more information on the material behavior.
Yeah, I know this is generalized, and I think it's let's say it's mainly deformation. Like there's a lot of utility. I mean, this is my experience seeing a lot of utilities. Some of these experiences in structures. So from a deformation, like what kind of lab tests would you like to see? Like I said, I mean, the goal would be like, hey, owner, we think we need these tests.
I would love to have some triaxial tests. Drained, undrained, anything that I can get some stress path from it, that would be lovely.
And I'm not against lab, but in general, the way I see the lab is very limited. If you have a big site and you have soil variability, where does it end? How many labs and what type of labs and how much time does it take? So, of course, we can debate this until the end of time, but at the end of the day, you need to kind of select the test that, in my opinion, gives you the best or the most information that are valuable for the project. Maybe I will lose something with the CPTs, but I get a much more wider range of information also on soil variability. That is my point of view.
Damian, what do you think is achievable that you can get? I mean, that's some of the, tests are expensive. Exploration, the more maybe locally, what is more typical nowadays?
Yeah, so Boston is it's kind of interesting given the history of Boston, all the large infrastructure, private development projects that have gone on. CPTs are tough to get. Cone Tech is not that I'm plugging Cone Tech here, but they're going to open a Boston office, but we don't have a lot of availability of CPTs. And the other thing, just in the Boston area, is depending upon the projects, a lot of times we need deep foundations. It's really tough to get the CPTs in this area, through those glacial soils, or impossible. So it's a combination, right? It's what can we reasonably convince the owner that this is the minimum that we need in order to get you the right answer. I think oftentimes it's a combination. It's a combination of SPTs because just locally they're much more readily available. CPTs when we can get them up there and afford the mobilization costs, and lab testing to correlate those CPTs or those SPTs. And big fan of pocket penetrometers. Not even a laugh? Nothing? All right, thank you. I'll take what I can get.
You know, I would say also, for the lack of information that we gave you, yes, you did an exceptional job.
Yeah, I would agree with that.
No more borings. No, it was very good. I was impressed. What questions do we have? Jeff?
Well, I take some blame for coming up with this basal heave idea.
It is your fault.
Yeah, it came after watching Whiston give a presentation on some of the charts that we saw Damian give. I'm going to just, she had mentioned 3D effects, and we tried to just set up plane strain just to make it simple. But I'd like you to comment on maybe 3D effects to mitigate heave as you're seeing it. Have you seen experience of that? Do you think it's, that you could model that pretty effectively? I'll just throw that to the panel about 3D effects and how it fits on that.
Gosh, how much time do we have here? So I would say that, yeah, 3D effect is important, probably is not so important in this case. You may have some mitigation in the corner. I would say that in my experience in deep excavation, if you are concerned about heave, probably you wouldn't go with a wide open excavation all the way through. You try to minimize the time of the excavation, and you try to install preventively some kind of a anchoring that would control the potential heave that would manifest. So in a case like this, if it was possible, probably top down with final piles installed since the beginning, like the example that Damian was showing this morning, would help to kind of capture at least two pieces of the equation. One is the control of the heave, and the other one is a stiffer structure and not have any problem with bottom instability. And so if you can, that would be probably the best option. Otherwise, what I did in some cases is when the heave was important, you have to go, I install, for example, fiberglass pipes, temporary fiberglass pipe. You have very weak soil and you need to go down, and you install preliminary this fiberglass pipe that would help in tension to control the heave. Another solution, if you really have something that is very, very poor, you go with dip mixing. Or you have to improve the soil instead of relying on 3D, which is still very uncertain.
Okay, the models that we showed you, all of us, we had the whole layer across the span of the model excavated in one go. If you are going 3D, probably you're not doing that in real life. You have different geometries, different section. You might excavate different section. You might do different, you might consider different things happening there in terms of excavation and support. So if there was more information of the process, I would go 3D to consider those. So that's why what we showed here, 2D and 3D, they did not differ a lot. It was almost the same thing. It was just extruded. Okay, I have the corners, but the corners were more stable than the sides. So if you have 3D construction stage, yes, then you can control the heave the way that you need to, and you can simulate it the same way.
That's why we only gave you one boring. Couldn't, like, I mean, I once again, I think the benefit of 3D on especially a large site would be the variability. And with CPT, being able to do multiple, the 3D analysis, I would think, that would help.
If it was a real example, you have a bunch of information boreal and you try to build a subsurface map and then accommodate into the 3D model the subsurface condition, like I was showing for the TPI project, where we have, almost, 200 or something boreal, and we build the subsurface condition, because in that case, soil variability was very, very critical. Maybe in an urban area is less critical. Boston, you have a couple of feet of variation is not so important, but in certain cases is really important. So it really depends on the site.
Yeah.
Alireza?
Yeah, Alireza, I'm sorry.
No worries.
Your estimation of soil investment.
Mhm.
What was your estimation
The one that I ended up using at the end of it was a 40 feet excavation, 20 feet embedded.
20 foot.
Yeah.
Thank you. Speaking about 3D effect, 3D effect, in my experience, it's not just about the soil profile. When you have a big excavation, 3D effect comes from how you excavate and when you put the mass slab and how you do the construction sequence. I have one project in very soft clay in 500 foot wide, 500 foot wide, with about 50 foot of excavation. At the time, people said there'll be a big problem, but we estimate the construction time, sequence the excavation, sequence the mass construction. So we were successfully did excavation without doing, holding down anchoring system. So I think the 3D effect and transient nature of the soft clay or clay has to be considered to be a little bit more effective design or simulation.
Yeah, completely agree.
Yeah, I agree with what Miak was saying. A lot of times the way we use it is we'll do our 2D analysis first, right? And when we have issues with the 2D analysis is when we tend to break out the 3D analysis, especially when it comes to bottom heave and stuff like that, to really try and fine tune and work with the contractors to be like, all right, well, what is that construction sequence? Can we sequence this mat? Can we leave this portion of the site high, pour this one, and just work in sequence so that we don't have to do subgrade struts, deep soil mixing, fiberglass rods. Of course. And but it's a very helpful tool in identifying that and identifying where you can, kind of optimize the system.
That's why I left preliminary title of the presentation, because it's the first round, and then you sit with the contractor, and partial excavation in a site like this would happen anyway, because you're not going to open everything at the same time.
Good. What else we have?
Kind of going back to the start of the presentation with Damian's global settlement problem, not being able to predict it with sort of more typical finite element. Coming from like an embankment dam background, it seems like the side that's missing is a more in-depth seepage analysis. And I know I don't work directly with Boston blue clay. I spent a little bit of time in the Boston area, but I know it's a varved deposit. So I wonder if kind of the way you're modeling the recharge, sort of the distance from the excavation where things are recharging, it's very close because we're only looking at deformation. So we think, we only need 100 feet, 200 feet or whatever. But if you kind of consider more of like the global changes in pore pressures from excavating 40, 60 feet over this bigger and bigger area, that small change in pore pressure over a really deep soil profile in a large area may generate that sort of global settlement that you're seeing. So I don't know if anybody's thought about that. But
yeah, I would say that there is definitely a seepage component. I'm not sure how that would impact. And in the model, it was kind of showing clearly that the curve was tapering off, but was not going to zero. So clearly the boundary was too close, even for deformation analysis. So in a real example or in a real design, I would put it a little bit further away. It depends also if we are, again, in the Iowa cornfield or in Rome beside the Colosseum. So that also has an impact. But yes, it is a good point. It's also very difficult to estimate because the anisotropic impermeability, site variability becomes even more, I would say, important for flow analysis and also time-dependent analysis. Because this is transient, and we don't know exactly how this material behaves unless you do some field tests somehow in terms of pumping, measure the settlements, let it recharge and see how it behaves. It's very difficult to have those kind of information at the scale of the project. And looking at an odometer is pretty much nothing. So, no, I totally get your point, and it's a good point in my opinion, yeah.
Yeah, I think it's something that it depends upon the project and the sensitivity to it. The project that I spoke on earlier in the afternoon, we actually took that into account. We were very concerned with that from less so from a stability standpoint, but we went out and did pumping tests, and the models that we developed and ran, not all the ones that I showed, we went out a couple thousand feet to really understand those impacts because of how critical it is. But it's very project dependent from my experience.
Following up on that, are you seeing that the depth of embedment is controlled more so by heave stability concerns or by pore water pressure and seepage concerns?
For in the Boston area?
Yeah, for what you've seen, Damian. That's
it's stability. It's stability. The Boston blue clay isn't real permeable. doesn't let out a lot of water. We do have occasionally thick sand layers above top of that, and depending upon where you're excavating, and we do have parts of Boston or the greater Boston area that has a lot of interbedded glacial geology, and that sometimes becomes a real driving factor. But for the the typical Boston blue clay, it's really just the strength and that strain softening and the stability.
If I may add to that, throughout the simulation that I did, the effect of unloading of the excavation on the pore water pressure was way stronger than water flowing in. It was more generating negative pore water pressure because of the suction from unloading.
Yeah, it also depends, kind of a trigger, another point, which is it depends on the, let's say, the coupling between the soil and the fluid phase, which is also mixed with air. So the bulk modulus of water that we use in these analyses is never 2 gigapascal, which is the ideal modulus, bulk modulus of water, but is 2 order of magnitude less, even more than that. So this is another uncertainties that we have to add on top of all the other uncertainties that we already have. So this negative pore pressure, I also saw negative pore pressure, but in reality, when I've been able to monitor this negative pore pressure, we're in the order, most cases in the order of 20, 50 kilopascal, even for big excavation and in very, very impermeable clay like the Vatican clay or the London clay, relatively small in comparison to what you would predict if you assume a high value of bulk modulus. So that is another parameter to keep in mind.
Any other questions? I have one final question then about it. Where the future of this type of analysis, growing, I think, or required due to the sensitive nature of pressure building around. But where do you want to, the aspect of it, where do you want to see it go in the future? From like an educational standpoint, a use standpoint. I think one would be getting better data on a more consistent basis. That's what I would say. But I didn't. What are your thoughts on down the road type of analysis?
Just very simple. One thing that I still see and is a little bit depressing, quote unquote, is that sometime on the owner side or some parts still see these analyses more, oh, we have to do it because we have to do it. But they don't really appreciate the value in terms of optimization and in terms of understanding potential risks. So it also ties in with the risk management. It ties in with the optimization. And so at the end of the day, you kind of economize the project, optimize the project, and also better control the risk analysis. And this is the message that, in my opinion, is still weak outside and is still perceived that you can just walk away with a kind of a hit of a button, garbage in, garbage out type of mindset, which is true, but still the way I see this type of analysis is more of a numerical lab, the way you would experiment, the way you would kind of gain confidence into the problem and then guide for also other investigation or other type of information that you may lead. So I tend to be, I'm definitely biased in that sense, but I hope to kind of convey this type of message for the future.
I would say this numerical simulation that we do is not one shot. I did the simulation and we are done. If we can incorporate the simulation and evolution of it and calibration of it throughout the process of construction of the site, that would be very beneficial to everybody that is involved in it. So I would like the process to be like practiced and get normal in the engineering community. So you have these tools, Itasca, Plaxis, RS2. There are very good tools. They have various functionalities that you can utilize. But using them as the process goes and you calibrate your model, it can help you predict better behavior. You can use those data to better analyze and better do your construction. So if the process is developed further and further, that's I would appreciate that.
Yeah, I'd agree with is on that as well. I mean, the tools have become so powerful and so easy to use, to be honest, that as long as you have the right people with the right data being input into them, just think about how much more efficient we could make our construction during the process, both to the standpoint of reducing that construction costs by eliminating elements that aren't necessary. There were talks given of, oh, we installed these piles because everyone said we had to do them, but we don't really think we need them. Well, if you're doing excavation or doing installation or doing construction, and you can prove through the modeling that the construction is behaving, the soils are behaving as you've modeled, you can maybe pull some of that stuff out. Or at the other side of things, things aren't behaving as well. I sure want to know that in advance so that I can deal with it. And I can deal with it proactively, as opposed to now I'm at the bottom of my excavation, and that building over there is sinking into the ground, and there's nothing I can do anymore, except for hire a good lawyer.
That session was yesterday.
Yes, it was. That's right. That's right. That's right.
Okay. I mean, I don't know if there's any other questions, but we can probably conclude now. I would like to say give my appreciation to Damon and Alireza, Augusto, and all the effort that they put in to this work. Great presentation. Really was awesome. So one more round of applause.